Electrode potential. When a metal is dipped into a solution of its ions, an electrical potential is set up between the metal and its ions. For example, zinc is dipped into a solution of zinc sulfate. So in this solution, there will be zinc ions and there will be what? SO42 minus ions. But the potential gets set up between zinc atoms in the electrode and zinc ions in solution. What we call potential is a tendency for the zinc atoms to form that's a tendency for the zinc atoms to either form zinc ions or for the zinc ions in solution to gain electrons and form zinc atoms. That's what we call electrode potential. But what happens in the case of zinc in a solution of its ions is that the zinc atoms from the zinc rod actually lose electrons. Zinc atoms from the zinc rod lose electrons like this and become zinc ions in solution aqueous because of the high reactivity of zinc. So that's what is referred to as electrode potential. When a metal is dipped, let me read from the notes I have here. When a metal is dipped into a solution of its ions, a half cell is set up. We call that half cell, sometimes we call the half cell an electrode. A half cell or an electrode is formed. In this half cell, a potential exists between the metal and its ions. This potential is called electrode potential. For example, in the diagram above, when zinc is dipped into a solution of zinc ions, some zinc atoms from the zinc rod lose electrons to form zinc ions, as shown in this equation. Some zinc atoms from that zinc rod lose electrons to form zinc ions in solution. Let's continue. Also, when copper rod is dipped into a solution of copper ions, the copper ions in the solution gain electrons and get deposited on the copper rod as copper atoms. So it's an opposite thing that happens when copper rod is dipped into a solution of copper ions. For example, you can dip copper rod into a solution of maybe copper nitrate. Let's say you dip copper rod into a solution of CuSO4 copper sulfate, or your solution can be CuCl2 copper chloride, or CuNO3 copper nitrate. The same thing will happen in this case. There will be a potential set up between the copper ions here, Cu2+, and the nitrate ions. And the copper atoms. There will be a potential set up between the copper ions in solution and the copper atoms present on the rod. So at the end of the day, it is the copper ions present in solution that will gain electrons and get reduced and deposited as copper atoms. That's what happens with copper dipped into a solution of its ions. The electrode potential of a metal can be measured by connecting it to a standard hydrogen electrode. We can actually measure the electrical potential set up when any metal is dipped into a solution of its ions. We can actually measure the electric potential set up when any metal like this is dipped into a solution of its ions. We can do that by connecting the half cell of that metal. For example, this is a half cell of zinc. We can measure the electrode potential of zinc here by connecting this zinc to a half cell. By connecting this zinc to a half cell of hydrogen. You will see that in a while now. But that's what we do when we want to measure the standard electrode potential of a metal. So you will connect a voltmeter here, connect the half cell, connect a voltmeter, connect this zinc half cell to a half cell of hydrogen, and then whatever the voltmeter reads will be the electrode potential, will be the standard electrode potential of zinc, because the electrode potential of hydrogen is taken as 0.00 volts. So when you do this connection of a half cell of any metal like zinc here to a half cell of hydrogen, which is called the standard electrode, your voltmeter is the electrode potential of the metal. Let's go ahead and see how that happens. Let's see how that happens. Let's look at the hydrogen electrode now. The hydrogen electrode is the half cell formed when hydrogen gas is in contact. It's the half cell formed when hydrogen gas is in contact with hydrogen ions. Just like a half cell is formed when a metal is in contact with its ions. A half cell is also formed when hydrogen gas like this is passed into a solution containing hydrogen ions. This solution contains hydrogen ions, for example, because this solution is a solution of hydrogen chloride. And hydrogen chloride will dissociate HCl aqueous. HCl aqueous will dissociate to H plus and what? Cl minus. So there will be hydrogen ions in the solution, and as hydrogen gas gets bubbled into the solution, the hydrogen gas come in contact with the hydrogen ions. So bubbles of hydrogen will be seen on this platinum wire inside the solution. So that way we say we have a hydrogen electrode. So to get a zinc electrode, you connect a zinc rod, you dip a zinc rod into a zinc solution. To get a copper electrode, you dip a copper rod into a copper solution. To get a hydrogen electrode too, you pass hydrogen gas into hydrogen solution. You understand? Or into a solution of hydrogen ions, just like HCl here, solution of hydrogen ions. So let's continue. Now, the hydrogen gas is passed in. The conductor in this half cell is the platinum wire here. The conductor is the platinum wire. The solution of hydrogen used is hydrochloric acid. Hydrogen chloride is a gas. They should have written hydrochloric acid here, but let's just take it as hydrochloric acid. Then the reaction condition, you understand, to make our measurement standard is a temperature of 25 degrees Celsius. The reaction conditions to make our electrode measurement standard, our potential measurement standard, is a temperature of 25 degrees. The experiment must be done at 25 degrees temperature. The concentration of the hydrogen ions must be 1 mole per dm cube, and the pressure of the environment must be 1 atmosphere. Sorry, the pressure of the hydrogen gas must be 1 atmosphere. So take note of these three conditions. Once set up, bubbles of hydrogen gas are seen on the surface of the platinum. Now, determination of the electrode potential of a metal. To measure the standard electrode potential of a metal, we connect a half cell of that metal to a half cell of hydrogen, as shown in this diagram. Now look at what we have here now. I explained this earlier. To measure the electrode potential of zinc metal, to measure the electrode potential of zinc metal, you connect a zinc half cell. This is a zinc half cell. All of this is a zinc half cell. You connect a zinc half cell over a voltmeter to a hydrogen half cell. All of this is what? A hydrogen half cell. You connect a zinc half cell to a hydrogen half cell. Ensure that the temperature of the experiment is 25 degrees Celsius and that this hydrogen solution is 1 mole per dm cube. It can be HCl, it can be another suitable solution of hydrogen ions. And that the pressure of this hydrogen gas, concentration is here. Ensure that the concentration of the HCl is 1 mole per dm cube and that the pressure of the hydrogen gas passed in here is what? 1 atmosphere. Once that is done, once those three conditions are fulfilled, temperature of 25 degrees Celsius or 298 Kelvin, gas pressure of what? 1 atmosphere. I'm emphasizing this because of its importance. And the concentration of hydrogen ions of 1 mole per dm cube. Once all this is ensured, whatever the reading of the voltmeter is, gives us the standard electrode potential of zinc. So the voltmeter, once this is set up, one of these will stand as the anode and the other will stand as the cathode. The metal that stands as the anode is the one higher up in the activity series. You understand? A salt bridge is usually included in the setup for 2 reasons. After connecting these half cells using wires like this, after connecting the half cells using wires over a voltmeter, we also usually connect a salt bridge to help maintain charge balance and also complete the circuit. But maintenance of charge balance is the main purpose of the connection of the salt bridge. Maintenance of charge balance is the main purpose of the salt bridge. So now, since zinc is higher than hydrogen in the electrochemical series or in the activity series, electrons then flow from zinc. Look here what I'm explaining. Electrons then flow from the zinc electrode to the hydrogen electrode. Therefore, the zinc electrode is acting as the anode where oxidation takes place. Oxidation always takes place at the anode, while hydrogen electrode is acting as the cathode where reduction takes place. Now, in this setup, we didn't give signs, but we have to give signs. Our zinc electrode is the what? Is a negative electrode, while our hydrogen electrode is the positive electrode. Now, electrons flow out of the zinc electrode. Electrons drift outwards from the zinc electrode towards the what? Hydrogen electrode. But electric current actually flow in the opposite direction. Electric current flows in the opposite direction. So we say electrical energy flows this way, but electrons actually move this way. So take note of that. Now let's look at the reactions that take place at each. Let's look at the reactions that take place at this. Take note of these signs. You will remember that in electrolysis, our anode is the positive electrode, while our cathode is the negative electrode. But this is electrochemical cell. In electrochemical cells, the anode where oxidation takes place is the negative electrode, while the cathode where reduction takes place is the positive electrode in electrochemical cells. This is an electrochemical cell. So let's go ahead and look at the reactions at each electrode now. This is the reaction at the anode. Zinc atoms in the electrode will lose electrons. Zinc atoms inside the electrode will lose electrons, you understand, to the circuit, and the electrons will lose electrons to the circuit and enter into the solution as zinc ions. You understand? At the anode, let me say that again, zinc atoms lose electrons and form zinc ions in solution. So the electrons lost will be passed through the conductor and drift into the what? And they will drift into the what? Into the hydrogen half cell. So this is oxidation. Everybody knows this. Loss of electron is what? Oxidation. So the electrons lost are passed around the circuit outside, are passed out of the zinc half cell and are, passed into the what? The hydrogen half cell. So on getting to the hydrogen half cell, hydrogen ions inside the solution will gain those electrons and form hydrogen atoms at the cathode. So it is two of these reactions that will occur to form 1 mole of hydrogen molecules. So that's how hydrogen bubbles are formed on the surface of the platinum in the hydrogen electrode. So what will happen is that you will start seeing bubbles of hydrogen here on the surface of the what? Platinum inside the hydrogen as cell. So this is the reaction at the cathode. This is the reaction at the cathode. There's an acronym we use in remembering what happens at each electrode. That acronym is called CRYO. You can jot it down somewhere. CRYO, standing for cathode reduction, anode oxidation. I hope you get that. CRYO means cathode reduction, anode oxidation. Cathode reduction, anode oxidation. So reduction takes place at the cathode and oxidation takes place at the anode. So this is the overall cell reaction. Let's now put the two equations together. This is what happens at the anode and this is what happens at the what? Cathode. So if we put the two together, electron loss at the anode or oxidation will cancel out electron gain at the cathode or where reduction takes place. So if you put these two equations together, only Zn. So when you put the two together, only Zn solid and 2H plus aqueous will, appear on the left side of our overall reaction. And that, in that process, zinc ions get oxidized. Zinc ions get oxidized and what? Hydrogen ions get reduced. Zinc ions get oxidized to form Zn2 plus, while hydrogen ions get reduced to form. So now let's continue. Sorry for that interruption. So on the left side, we have zinc atoms, and hydrogen ions on the left side. So the zinc atoms get oxidized to zinc ions overall, and the hydrogen ions get reduced to hydrogen gas. That's what happens in the overall reaction. Now, cell representation. These two half cells come together to form a cell. We can put the cell together like this. We always write the oxidation half cell first before the reduction half cell. And the two half cells are separated by double slashes, double forward slashes. So we separate, you understand? We write the oxidation with separate single forward slash like this. So zinc solid gets oxidized to Zn2 plus. We write that on the left and then write 2H plus. Are you listening? 2H plus get reduced to what? H2 gas. So that's how we represent a cell. So that means instead of drawing this big diagram, instead of drawing all this big diagram here, you understand? In chemistry, I could just represent the whole thing with this equation. Can you see how chemists have made things easier for themselves? I could represent the whole reaction with this equation. So anybody looking at this knows that this is an electrochemical cell. Anybody looking at this knows I'm talking about an electrochemical cell made up of two half cells. I'm talking about an electrochemical cell. This is the electrochemical cell, and that the electrochemical cell is made up of two half cells: oxidation half cell, reduction half cell. You understand? And that these are the reactions happening in each one. So to find the EMF of zinc now, we do the reduction half cell. We do the reduction half cell. We do the EMF of the reduction half cell minus standard EMF of the oxidation half cell. So since our reduction half cell is the hydrogen electrode, whatever we get here will give us the standard electropotential of zinc. And I think here hydrogen is 0.00 and then hydrogen is 0.00 and zinc is, I think, minus 0.76 or something. Yeah, zinc is minus 0.76. So at the end of the day, you get 0.00 plus 0.76. That will give you 0.76 volts. That's the EMF of the cell. You understand? That will be the EMF of the cell. But the standard electrode potential that will be measured for zinc here will be minus 0.76 volts. Minus sign. The minus sign indicates that the zinc gives out electrons to the hydrogen half cell, and that the zinc is a highly reducing half cell. A reducing half cell is one where oxidation takes place because it is supplying electrons. You understand? We call it a highly reducing half cell because it supplies electrons from itself to the hydrogen half cell. So take note of that. Now, the electrode potential, you can see here, the electrode potential of zinc is negative because zinc electrode loses electrons to the hydrogen electrode. So you take note of that, please. Let me turn up my light a bit more. Similarly, to determine the electrode potential of copper, connections are made as shown in this diagram. Can you see my connections? Same way, just that everything on the right is the same. Hydrogen electrode. Then we now have the copper half cell on the left. So it says, since hydrogen is higher than copper in the electrochemical series, I'm reading from here. Since hydrogen is higher than copper in the electrochemical series or in the activity series, electrons then flow from the hydrogen electrode to the copper electrode. You understand? So this is what will happen. That means the hydrogen electrode will serve as the anode in this reaction, and this is what will happen at the anode. At the anode, H2 gas will lose electrons to become 2H plus. So oxidation will take place at the anode. Anode oxidation. Take note. Oxidation always takes place at the anode. Then those electrons will flow into the into the cathode half cell. Those electrons will flow into the cathode half cell, and copper ions inside the cathode half cell will gain the electrons and get reduced to what? Copper atoms. So if you put the overall reaction together, in this case too, you will get something like overall you will get overall reaction. The overall reaction will be 2H2. The overall reaction will be H2 gas minus 2E to give 2H plus. You understand? From the anode, then Cu2 plus aqueous plus what? Cu2 plus aqueous. Cu2 plus aqueous plus 2E to give Cu solid atoms, copper atoms at the what? At the cathode, and overall you will get this at the overall. This will be your overall reaction. H2 gas, Cu2 plus aqueous. The two changes will be written down like this: 2H plus aqueous plus Cu solid atoms. So this is the overall reaction. If I want to represent this cell with an equation, let's now do that too. Cell representation. Okay, let me make that smaller. Cell representation. Sorry, I'm a bit fast. Cell representation. How do I represent my cell? To represent my cell, very easy. This cell is going to be represented as, I'll write reduction. What I need to do to represent my cell is to write reduction half cell and separate it with 2 slashes and write oxidation half cell. Sorry. What kind of mistake it is? Is to write the oxidation half cell I'll write my oxidation half cell on the left, separate it with 2 slashes. Sorry, my slashes are not straight. I'm a bit in error. And separate it from my reduction half cell. Separate it from my reduction half cell. So my cell will be written as, therefore, my cell, this cell will be written as oxidation half cell, that's H2 gas. Let me change the color of my marker. H2 gas slash 2H plus, that's my oxidation half cell, slash Cu slash what? Cu2 plus a gas slash Cu solid. So I've written my cell like that. You understand? This is my cell. My cell is made up of 2 half cells: oxidation half cell, reduction half cell. So if I want the EMF of this cell now, what do I do? If I want the EMF of this cell, the standard EMF of this cell is going to be the standard electrode potential of the reduction half cell minus the standard electrode potential of the oxidation half cell. That will be what? That will be, okay, I'll just go to a table of values and read them off. You understand? Read off the standard electrode potential of hydrogen. Read off the standard electrode potential. Read off the standard electrode potential of copper. Sorry, copper is the reduction half cell. Read off the standard electrode potential of hydrogen, which is the oxidation half cell, and subtract. Then I'll get the EMF of my cell. So let's pause here for now. In the next video, we'll look at a few examples, see how cells are set up, and answer some very important questions.